Bien, les damos la más cordial bienvenida a esta nueva sesión de nuestros online meetings, como lo hemos llamado, donde hemos hecho un trabajo conjunto entre la iniciativa W-ENER, de presentaciones, ¿cierto?, de seminarios que ha liderado la Universidad de Talca, con el Distinguished Lecture Program de SERC Chile, y estamos muy contentos de poder llevar esta acción conjunta junto con las instituciones y empresas que han apoyado esta iniciativa. Así que hoy día es un honor para nosotros presentar a nuestro invitado, pero voy a dar la palabra a la profesora Claudia Raman de la Universidad de Chile, que a su vez es directora de SERC Chile, quien va a tomar la palabra para poder hacer la introducción de nuestro invitado. Muchas gracias, Claudia. Adelante.
Thank you very much, Rodrigo. I'm going to switch to English so our invited can understand everything. So thank you very much for being here today, and thank you very much, of course, Pouyan, for accepting to present today. Pourbeik received his bachelor and PhD in electrical engineering from the University of Adelaide, Australia, in 1993 and 1997, respectively. From 1997 to 2000, he was with GE Power Systems. From 2000 to 2006, he was with ABB. From 2006 to 2016, he was with EPRI. Since 2016, he is with Power and Energy Analysis, Consulting and Education. He previously served as both chairman of CIG Study Committee C4, System Technical Performance, and the IEEE Best Power System Dynamic Performance Committee. He is a professional engineer in Texas and North Carolina, US, a fellow of both IEEE and SIGRE, and an honorary member of SIGRE. The presentation of Pouyan today will briefly cover the types of converter interface resources currently in use in the industry, including wind, PV, battery storage systems, and hybrid plants, and will discuss the dynamic performance of such systems. It will then touch on the overall dynamic performance of power system dominated by such converter interface resources, and some of the challenges and solutions for such high penetration levels. He will give us also a brief overview on the types of models available in the industry and how and where they can be applied. So I would like to thank you, Pouyan, very much for your time again. You are very kind accepting to participate today in this wonderful initiative from University of Talca and SERC Chile. So now you have the control, you can present your slide. Thank you very much.
Thank you. First of all, just thank you, everyone, Claudia, and the university and SERC for this opportunity. It's my pleasure and privilege, and I hope it's, after the presentation, worth your while. So thank you for your time. And let me share my screen. Can you hear me okay, by the way?
Everything okay, Pouyan.
Okay. And with your permission, I'm going to stop my video. That way the bandwidth won't be a problem. Oops, let me go to the top.
Me hice un blend de música con la cámara y
okay. So as Claudia said, we're going to try to cover briefly these few subjects. And of course, it will be brief because obviously we could spend a day on each one of these things. And at the end, I'll try to afford time for just Q&A, and we can all dialogue together and learn from one another if there are questions. So as Claudia put it, I'll try to cover the main types of converter interface generation. So this CIG means converter interface generation. And then just briefly, the dynamic performance and challenges with high penetration of converter interface generation. Then what are the kind of models that are out there, and where and how are they used? So, and some of this, I'm sure many of you already know, so apologies for kind of covering some basics, but want to make sure we're all on the same page. So in terms of wind generation, we all know there are these 4 types, and I'll briefly cover what type 3 and 4 are. little bit more detail. Those are the ones that are converter interface generation. The so-called type 1 and 2, which are the earlier technology, where it was just a straightforward induction generator directly connected to the grid, running at super synchronous speed. Those are not manufactured anymore. They're not sold anymore for large integration into grids. You might find little small ones in the distribution system, but large vendors do not manufacture those anymore. You cannot even buy them. Now, here in the US, we still have a lot of those type 1s and 2s from 20 years ago when they were put into the system, but they're slowly going away. And the type 3 is the doubly fed asynchronous generator. So what it is basically, and let me see if I can get the pointer working here. So basically you have a back-to-back converter that links the rotor circuit of a wound, rotor machine to the stator. And basically what that allows you to do is very tightly, very quickly control the rotor phaser. And so in effect, you can control the P real power and Q reactive power coming out of this machine very tightly. And the type 4 is when you put a full powered converter and you basically decouple the generator from the grid. So now everything is controlled by this converter, and it's very tightly controlled, and you can do anything you want with P and Q, basically, within the ratings of the converter, of course. And these machines can be permanent magnet machines, like in the case of vendors like Enercon, or they could be a asynchronous machine like Siemens. And so basically this machine can be any variety of machines. Then we have photovoltaics, and I think this is the main thing that goes into your system in Chile. Correct me if I'm wrong. You have a lot of good sunlight. So this is just basically solar panels connected by a converter. So you only have one inverter now going from DC to AC. You may have a DC to DC converter here as well, just to control and regulate the DC bus. But basically, again, you have this converter interface that is fully controllable, and you can control real and reactive power independent of each other within the current rating of the inverter. And most of these, the large ones anyway, will have some sort of solar tracking system like the one in the picture here, where these panels will follow the sun, essentially track the sun. And then obviously at the end we have battery, which is now becoming more and more predominant. And battery again is, you have a power converter that connects the battery to the grid, and again what we call 4 quadrants. So if this is reactive current and this is active current, you can control this thing within this circle, where the circle represents the full current rating of the converter. You can operate anywhere in this region and very quickly go from one point to another. You have full control of P and Q independent of each other, so long as you stay within this circle. Now, when you hit the circle, you can have either active or reactive priority. That's something you may have heard from many vendors. What that means is during, say, for example, a fault or some event, they give priority to reactive power or active power, depending on your grid code. So at the heart of all these technologies is this power converter, and that's really what drives the dynamics, if you will, of these devices. Whereas in the old world, we've been used to synchronous machines, which behave completely differently, of course. And so this is a kind of simple diagram to try to illustrate that difference. So in the case of a synchronous machine, we have a rotating magnetic field on the rotor of the machine, and we have a rotating magnetic field on the stator, which is connected to the grid. So you could think of this as the grid phaser, and this is the rotor phasor. And obviously this angle between the two is the indicator of stability, right? We all know the classic equations that if this angle goes beyond 90 degrees, then we lose stability. And if this thing oscillates, and doesn't have damping, it can go unstable. Well, all those things are controlled by the excitation system and the turbine governor, right? So the excitation system gives us this synchronizing torque, which allows this angle to quickly come back into synchronism. We have a power system stabilizer to stabilize the oscillations. And then we have a turbine governor with primary frequency control to regulate frequency and keep the balance between active power and load. Well, now we come to these converter-based stuff. And now, in the case of the type 3, you still have a phasor on the rotor, but this phasor is now controlled by the power converter, and it's very tightly, very quickly controlled. So there's no longer this idea of transient stability because you lose rotor angle. It's very tightly controlled. And in these cases, this phasor is basically a phasor created by this voltage source converter at the interface. So again, the concept of transient stability in this same context doesn't exist. What now is important is you have a fault. Can the inverter ride through the fault? Can you make sure that the power electronics is not compromised, that you can come back after the faults and with the phase lock loop, lock onto the grid and get your phasor going. So it's a different dynamic altogether. And we'll talk about in a second what are the stability concerns in a diagram. But the concept is now this phasor is controlled very quickly by power electronics, right? So can they still do all the things a synchronous plant can do? Yes, they can still control voltage. So here's a real life example of actually doing a voltage step test on a large wind plant where you have, tens, I can't remember the exact number, but maybe 100 turbines distributed through a collector system. One of them is on one large substation transformer. The other grouping is on another large substation transformer. There's an overall power plant controller controlling all these wind turbines. And so we asked to change this voltage at the POI with a step change, and it did. And we stepped it back, and the blue is measurement. So this is actual megawatts coming out of the plant. Obviously, as wind speed changes, the real power is changing. In our simulation, we assume constant wind speed, so nothing changes. Here's the reactive power coming out of the plant, and here's the voltage, and you can see the blue stepped, and the simulation also matches quite nicely. In this case, the model is one of these standard models, what we call second generation generic models. And here, real life examples, these are photovoltaic plants, so PV plants. Can they do frequency control? Yes, they can. What it does mean is, though, that you have to operate the plant suboptimally. What I mean by that is you can't generate all the incident solar radiation into power onto the grid. You have to operate at a suboptimal point, not be at your maximum power tracking point, so that you have some megawatts in reserve. If you do that, then you see here, this was actually played into the plant to make the plant think that frequency dropped and then came back. And you see this is megawatts. Megawatts did increase and then came back as the frequency recovered. So you had primary frequency response. And then here, the frequency was played in to simulate frequency increasing, and you see it dropped and then came back. So you can have frequency response. Obviously, in this case, you don't have to have anything in reserve. It could be a maximum power tracking point because you're just decreasing megawatts out of the plant. But if you want to have ability to respond to an under frequency event and you don't have any, say, battery energy storage or anything in the plant, then you must always operate suboptimally, keep some megawatts in reserve. And that has obviously economic consequences because you're not generating all the power that's available to you. So I kind of summarized here, if you will, at a high level, what the implications of frequency response are for these technologies. And you can do, I haven't put the plot here, but I've got plots. You can do the same thing on wind plants as well, of course. So on wind type 3 and 4, can you do voltage control? Yes, you can. You can do it very fast. Can you do primary frequency response? Yes, you can, and you can deliver it in seconds. Is there an opportunity cost? Yes. What I mean by this is, as I mentioned, if you want to do primary frequency response on, for example, a wind plant or a PV plant, you have to keep some of the incident wind energy or solar energy in reserve. So that means you're not generating the maximum available incident energy. And so you're kind of losing some money because let's say if there's 100 megawatts worth of wind energy hitting your plant and you're only generating 90 of those to keep 10 in reserve, well, that 10 is lost opportunity cost because it's not going to be there forever. When the wind dies, it'll go away and you've lost the opportunity to sell that power. So there's some opportunity cost in that case. Can they do fast frequency response? I didn't show the example, but we have field measurements of that as well. And the answer is yes. You can take some energy out of the rotating inertia of the wind turbine and inject that into the grid. So you can do an inertia-based fast frequency response. There are consequences to that, and there are caveats to it, but it can be done. That doesn't have an opportunity cost for wind because that inertial energy is always available. But in the case of PV, that fast frequency response, again, does have opportunity cost because, again, you have to operate suboptimally to be able to inject that. But if you had battery, you can do all these things and there's no opportunity cost. There's capital cost because you got to buy the battery and put it in the plant. But once you bought it and put it in the plant, you've got that energy stored and you can do with it whatever you want. So these days, you'll find a lot of projects are going with this hybrid option. And here's the ultimate, if you will, hybrid example where you might have wind turbines in the plant, PV in the plant. There are real life projects like this today, and then battery. And so now you have the best of all worlds. You can do whatever you wish, control P, Q, V, primary frequency response, fast frequency response. And each one of these elements may have its own, obviously each one will have its own inverter level controls, right? And then the wind portion of the plant will more than likely have its own plant level controls. And the solar portion of the plant will have its own plant level controls for the solar. And then you will have an overall plant controller that controls everything. And then you can regulate voltage at this POI. You can have primary frequency response. You can have fast frequency response. You can do all of those. One other thing to just talk about briefly, and there's some public references there you can go to from EPRI, where this is taken from, and there's a paper that was recently published together with EPRI. Again, that's public, you can go look at it. So there's this new technology now that people talk about grid forming, and there's no one grid forming technology. There's many of them. Here we're showing 5, and believe me, there's even more. But I'll just talk very briefly about these. So this one is called a virtual synchronous machine. This actually, there are vendors that will supply this, and there are projects in the world in microgrids and even large grids now that have this kind of technology in place for battery energy storage and even PV. And this, basically what it does is that it removes the PLL, if you will, and now you have machine equations essentially implemented here to kind of control that voltage phasor based on emulated, if you will, inertia and rotor angle. Here you have another option, matching control. Then you have this droop-based control where what you're doing is, again, you're controlling that phasor, but you're doing so through a droop of active and reactive power to tightly control voltage and power. And the droop-based control can go two ways. It can use P and Q as an input, or V and speed or frequency as an input. Then you have this virtual oscillator where you have a virtual oscillator inside the controls, and based on that, you use that as your source, if you will, frequency to control the converter. And what does all this mean? If we look at the grid following, so this is the technologies primarily deployed today and has been for decades. What you have is you have your main circuit of your converter. Then you have a very fast, tight regulation of the currents, the active and reactive current coming out of this converter through a current regulator. And then you have a phase lock loop. The phase lock loop locks onto the grid phasor and then uses that to create a reference frame for all these controls to make sure that that internal phasor, remember we talked about back here, whoops, this guy, make sure this phasor is in sync with the phasor on the grid. So the PLL is the thing that's keeping you in sync, if you will. And then you're very tightly controlling the current here. Now, what that means is that's all good and great, but as the grid gets weaker, you may have to retune these controls to avoid instability, because high gains will create problems, and we'll talk about that in a second why. Whereas when you go to grid forming, because you remove that PLL, now you'll still have a synchronizing, circuit to synchronize the plant at the beginning, but once you're synchronized, then it's either this virtual synchronous machine or the virtual oscillator or the droop-based control that's regulating that phasor and making sure that the appropriate P and Q is being injected into the grid. And so by changing this control philosophy, now it's easier to keep stability under those weak grid conditions. The important note here is not necessarily to jump to the conclusion that that means everything needs to be grid forming. You could still have a stable grid with a combination of conventional generation, grid following, grid forming, or any perturbation of the above. The key is proper modeling, analysis, tuning to ensure stability. So let's talk now about dynamics. So this is a diagram I borrowed from a recent IEEE task force, and Claudia was the secretary of this task force. So, if after the call you have questions, you can always approach her. She knows all this stuff. This diagram basically just illustrates all the kind of stability issues we may be concerned with in a power system. Now, traditionally, we've always had these three, frequency stability, voltage, and rotor angle stability. But now with this higher penetration of converter-based generation, we start to get into converter-driven stability. So that whole thing I talked about right there of the stability of this controls here. And we may also have resonant stability. So those very fast controls may interact with other devices on the grid, like let's say if there's a HVDC nearby, or if there's a series capacitor, we might get a resonance between the asynchronous machines magnetizing reactance in the series cap, and the converter controls may introduce even more negative damping. So we have to look at those kind of phenomena. As we go to full converter-based generation, we remove all synchronous generation. If that happens, this rotor angle stability will go away, and now it'll all be all this stuff and this stuff, right? But so as long as we still have some remaining synchronous generation, this doesn't go away either. We still have to worry about rotor angle stability. And these dynamics are much faster, obviously, than these guys. So this is another way to look at it. We have all these time frames of phenomena, very fast transients like lightning, and faster transients, switching transients. Our control interactions with the converters might even be in here somewhere. Then, as we just said, SSR, transient stability, small signal stability, frequency control, and then longer dynamics. And then, depending on what we're trying to study along this time frame, we may need different models and different tools because of the bandwidth of things that are involved, right? Now, what are the challenges with weaker grids? As your system gets weaker, and let me quantify that. So as the short circuit strength, so synchronous machines naturally give you short circuit current, right? So when we have a fault, it just naturally gives us short circuit current. And there's no inherent current limiting device other than the internal impedance of the machine. So if, say, your subtransient reactance is 0.2 per unit, then you could get as much as 5 per unit current, right? So you have a lot of short circuit capability with synchronous machines. As you start to remove synchronous machines and you replace them with these converter-based generation, which are current limited and the current is very tightly controlled, your short circuit levels drop. You could think of that also as the effective impedance looking into the grid increases. So you get a larger, if you will, Thevenin impedance looking into the grid from a node, like a plant. Well, if this impedance is getting larger and larger, what that means is for a small change of current injected into the grid, I'll get a large change in voltage. And so it becomes more and more difficult to control voltage, and therefore you lose gain margin on your closed loop controls. And similarly, you lose gain margin because frequency changes much faster. You'll lose gain margin on things like your PLL trying to lock on to the frequency after an event. So tuning of controls become much more important, and you may need lower gains to make everything work. And at some point, you may need to have something else to help you, and that's where some of these potential solutions come in. That you may need to increase short circuit strength. So one of the things that are actually being done in systems around the world is you introduce synchronous condensers to increase the short circuit strength in a region where there's a high penetration of CIG. But there is a limitation to that as well. If you put too many synchronous condensers, remember they are synchronous machines, you may start to get rotor angle stability issues with those and have to find ways to mitigate that. So there's a balance there. You can't just keep putting more and more synchronous condensers. Another option is to retune the PLL and intercurrent control loop for the weaker conditions. Move towards grid forming inverters or all of the above. You may need a combination of all these things. Some grid forming, some retuning of PLL, a couple of synchronous condensers placed strategically in the system. And one of the other things, I skipped that, let's go back up here. As your short circuit levels decrease, protection becomes more challenging. And I'll confess, I'm not a protection engineer. I probably know enough to be dangerous. But there are these reports, and IEEE report on YouTube you can go to where we discuss that. And the issue there is obviously because these converter-based generation are very tightly current regulated devices, you're not going to get those like with the synchronous generator, 3, 4, 5 per unit short circuit current. And so it becomes more difficult to distinguish between a fault and continuous current, normal current flowing on the line. So you have to get more sophisticated and kind of find new innovative ways to protect. Or if there are issues, again, the synchronous condenser can provide that short circuit current. So this is another challenge, is protection. The other thing with protection is distinguishing between balanced and unbalanced faults. That's one of the reasons you would have seen and probably heard there are now talk of, and certainly in Germany they've started doing that, of asking the converter interface generation to actually provide negative sequence current during the fault. So what are the needed functionalities for these converter interface generation? It's pretty much all the same stuff we've wanted from conventional generation: Var control, primary frequency response, the potential need for fast frequency response, low high voltage and frequency ride-through reactive capability. And as I showed you in a couple of quick examples, all these things can be done, and they are being done by the technology. There's a standard right now, it's currently under development, called IEEE standard P2800. It's a draft right now, and it's gone through one set of balloting, and right now they're addressing the comments to put it out again. Jens Bomer from EPRI is the chair. And so that standard is making the first attempt industry-wide to set minimum performance requirements for all these kind of functionalities and much more, to be able to have some minimum standard by which this equipment is designed and available and has capability. So as it goes into the grid, it can do the things we need it to do. And as I showed you, they certainly can. So how do you model this stuff? Well, there's a hierarchy of models, and this has been true for conventional generation too. So these model groupings are nothing new. So at the highest level, the most sophisticated models are these hardware in the loop. And as I say, it's been done even for synchronous generation. I've worked with these at GE years ago. And what it is basically you're taking the actual hardware, so the converter controls and all that stuff, and you're hooking that actual hardware to a computer that simulates, let's say, the grid. And so now you can do all sorts of things, simulate faults and play all sorts of games. And so you have a hardware in the loop plus a simulation of the grid. And these are obviously proprietary. Utilities will sometimes work with a vendor to buy it and actually set up in a lab of their own. There are entities that do this, and so you can do really high-level design and commissioning tests with these things. The next layer of modeling is three-phase models in EMT tools, electromagnetic transient tools. So it's either EMTP, ATP, PSCAD, those kind of tools. And so again, these are typically proprietary, but certainly shared with utilities and consultants and what have you through non-disclosure agreements. And the emerging method for doing this is you have a DLL-based model, which is created by compiling the actual source code from the hardware, and then you link that into the EMT model. And then you go to the next layer, which is your positive sequence model. So in tools like PSSC, PSLF, Dig Silence, RMS feature, PowerWorld, TSAT from Power Tech Labs, Eurostag, what have you. So those, again, you can have vendor-specific models from the vendor, which again can be this DLL-based, which could be literally the same DLL they link into the EMT is linked into the RMS tool, or it could be written in the native language of the RMS tool in Fortran or C++ or what have you, and compiled in. The idea here is, again, it's vendor specific to the control strategy of the vendor. And then last here are these generic positive sequence models. There are two sets of those. There's the IEC standard models for wind turbines. Then there's the WEC second generation generic models that cover wind, PV, and battery energy storage, and to some level hybrid. And these can be parameterized in many cases to be quite useful for grid stability analysis. The key is understanding, what is the task, and therefore which model do I need? Obviously, properly parameterizing it. I think this to me is the biggest key, is communication between, transparent communication between the vendor, the plant owner, and the transmission owner operator, so that everyone across the board understands which model is the proper model for the task, parameterizing it properly, and knowing what you're doing. Now, obviously, if you're studying something futuristic, let's say you try to study a 2050 future scenario, you have no idea what vendor or what equipment, then the best model are these generic models. You can take them, parameterize them to reasonably represent a wind plant, a PV plant, or hybrid, or what have you, and do some studies. But again, reasonably parameterized, properly parameterized. But let's say you are looking at a particular site and it's close to a series cap and you're worried about SSR. Well, then you need the vendor-specific EMT model, and you need to go in there and have this communication between the vendor, the plant owner, and the transmission planner to really study that scenario and make sure you can mitigate that problem. Or if you're worried about harmonics, or if you're doing insulation coordination, or even detailed site-specific controls tuning, those all require vendor-specific models, right? So it's really important to understand what it is we're trying to study, and then we can choose the right model for the task. So just real quick, some examples. This is a real system which is dominated by a whole bunch of wind plants. So in this case, we went through and one by one did step tests on the plants, and then appropriately parameterized the standard models to fit the plant. And actually the parameters were derived by looking into the software of the actual plant controls and taking the gains from there and properly per unitizing them to put it into the model. So we're not doing some sort of fancy optimization. We're actually basing it on the actual control strategy. And again, always, I'm sorry they're small, you can probably not read them, but this is real power at the plant level. This is reactive power at the plant level. This is voltage at the point of interconnection. And blue is measurement and red is simulation. It's good that they lie on top of each other, of course. So after having done that for all the plants, then we went in there and switched a large capacitor on the transmission system, and then looked at the response of each plant, and everything matched quite nicely. So that illustrated to us that we got a good match for each plant doing that. After that, we built a model of the whole system and switched the cap, and everything matched without touching any of the parameters. So that was kind of good verification. And if you zoom in, even at the very short time interval level, which is where the inverters at the inverter level controls are really kicking in, you still have pretty good response match. Here's an example where you're doing large signal response. This is a battery EMT versus positive sequence. And again, you see for balanced faults, you get a very good match across the board. For unbalanced faults, obviously, you don't get as good a match, particularly in Q. Why? Because, well, one model is positive sequence, the other one's EMT. And, you know, positive sequence, at least right now, cannot capture those, you know, the negative sequence components and whatnot, and so cannot really emulate what the controls are doing. What I'm plotting is indeed, you know, the positive sequence voltage and the three-phase P and Q. But the thing is, because it's a positive sequence simulation, it sees this as a positive sequence drop in voltage and gives the appropriate reactive response. Whereas in real life, the EMT controls, what it's seeing is that only one phase is dropping, and so it's that phase that's responding in Q and the others are not. So you basically a disparity between the EMT model and the positive sequence model. There are thoughts on how to use sequence network data to maybe improve the positive sequence models to be able to capture some of this stuff, but that's still kind of researchy phase. That's kind of it. So I'm going to stop there, and hopefully I didn't go over time, then afford some time for questions and answers. But just to summarize, you know, there are new challenges in systems with high penetration converter interface generation. I hope I touched on some of those. As we saw, these challenges can be technically solved. There are models that exist at all levels that we can go in and study these phenomena in detail. The key is always to understand clearly the objective and then the appropriate model for the appropriate task. I think it never hurts to emphasize how important it is to always have good communication amongst all the stakeholders, the vendor, the plant owner, and the system planners when you're talking about specific projects. So I'm going to stop there and just hand it back to, I guess, Claudia, if there are any questions and things we want to discuss as a group, or Rodrigo.
Yes, thank you. Thank you very much for this nice and very interesting presentation, Pouyan. And so we can start with the questions from our audience. And we have some questions in the chat. And let's start with the first one. So you can also make the questions in Spanish so we can translate and so we can move forward. From Francisco Mendez, could you please explain a little bit more the opportunity cost for battery? I think it's no neutral. For instance, if I have a BESS to make load shifting during the discharge injection of energy to the grid, I can do FFC. I need to reserve a fraction of power, same case of PV. So if you can elaborate of this conclusion that you make the difference between batteries and the other ones.
So Francisco makes an excellent point, and he's right. So I'll acknowledge his point. You're right. When you get into the details of it, a BESS may have opportunity cost as well, because if they install the BESS in the plant, like he's saying, for load shifting, or load shaving, sometimes it's called in the US. In other words, that when you have extra energy coming from the PV that you can't sell into the grid, you might store some of it in the battery, and then later on, as the sun's going down, you use the battery to inject power so that you keep the power out of the plant flat for longer and make more money. If you're doing those sort of things, then he is right. You now may not have the battery available for primary frequency response or fast frequency response. And if you want to, you have to reduce some of that or increase the size of the battery. So there's additional cost. So yes, once you get into plant design, there's all sorts of costs and economics you have to take into consideration. You're right. But
Great.
in the case of wind and PV, without battery, it's all opportunity cost. I hope that answered the question.
Yes, I believe, and you can start then a bilateral, because we have a second interesting questions regarding the direct power converter control and how it deals with these problems. And Sergio said, instead of the PLL-based control, this is if you can make a comparison.
Yeah, so, you know, the grid forming, as I said, the philosophy, the idea behind it is because you remove the PLL, now that can, I mean, that's actually been done for decades. If you go back, you know, one vendor I even work with, HVDC vendor for decades, has had this kind of, if you will, grid forming functionality for their voltage source converter based HVDC, where they can black start a region. So the idea is that because whether it's virtual synchronous generator or virtual oscillator, in a sense, you're creating that phasor and keeping that phasor inside the converter, then you are in a sense creating your own frequency. You can black start a region and you can tightly control that internal phasor. Whereas when you have a PLL, you always try to get your reference from the grid. And so in that case, as the system becomes weaker and frequency, therefore you have less inertia, frequency can change much faster, then the PLL has to keep up with that. And if it's high gain, you get into a stability issue with the PLL control loop. And that's the whole phenomena there. Now, does that mean everything has to be grid forming? I don't think so. There are actually regions of the world today where they have a combination of all these things and they can make them work. It's just a question of, you know, studying it in detail. Often when you get to these kind of things, you may have to go into EMT type models and making sure everything's properly tuned and performing well. I don't know if that answers the question. If there's more specific details you want to get into, maybe, I don't know, who is it? Is it Sergio? He can ask.
Yes, it was Sergio. And the next question is also related with this, because you connect this with the simulation tools for power systems dominated by converter interface generators. And the question is, in your opinion, what is the importance of using detailed EMT simulations instead of the traditional RMS simulations in order to correctly model the dynamics of future power system? Do you think that it will be practical to move from our RMS simulations to EMT simulations to study real large power systems?
Yeah, so this is a very hotly debated subject right now. So let me go back and I'll give you my personal opinion based on what I consider fact, and then we can discuss. If you would look at this diagram, so all this stuff I talked about, PLL and, you know, controlling the converter, etc., we're still talking about time frames that are somewhere in this region here, right? We're not talking about very fast dynamics. We're still talking about time frames in this region here. So we could simulate it at, say, 1 millisecond or half a millisecond time step, right? So that still falls, in my opinion, in the what some people call RMS, but more correctly, positive sequence phasor domain simulations. The key is to model those components, to model the, you know, if you've got a PLL to, whoops, I'm going the wrong way. To model all these things, if you model all these pieces, the current regulator, the reference frame, transformation, the PLL, and you can, then yes, you can study it in positive sequence. Or in the case of grid forming, if you model your droop-based or your virtual oscillator or your virtual synchronous machine controls, these dynamics are still in that bandwidth that you can study it at 1 millisecond or half a millisecond integration time step. You don't have to use an EMT tool with microsecond time step to simulate it. But if you're going into things like SSR, the issue here is that SSR requires you to also model the frequency, the frequency domain aspects of the network. So the frequency dependency of the network components, like your series capacitor, your lines, etc. That obviously is not done in positive sequence because we have a constant impedance matrix, right? So then you have to go to something like an EMT tool where you have frequency domain based line models and you explicitly model the series cap and so on. So again, my comment of depends on what you're studying. If we're studying only, these things, the converter driven stability that's associated with, let's say, these loops here, if we model faithfully these loops and we reduce our integration time step to the bandwidth of these loops, why not? Why can't? It's already been shown in some simulations and some of these papers I listed here. You can go to, let me see if I can find it. Hold on. This one, you can go to this paper and show an illustration of modeling, simulating 100% inverter-based resource grid in positive sequence with one of these virtual oscillator type controls. So I don't think we're ready yet to completely throw out RMS or positive sequence or phasor domain simulations. And Claudia, I know you and Rodrigo, you guys do a lot of research in this. You may have another perspective you want to share.
Yes, Claudia, if you want to comment, please.
Thank you, Pouyan. I think, like you said, this is a very high topic today in the international community. I agree with you in terms that it depends on what we want to study, of course. And I also want to believe that the positive sequence models are still good, even if you have a lot of converters. But I am really not sure about the dynamics. Yeah, when you have, for example, a 100% converter-based power system, in that case, I think we need to move more to in the line of electromagnetic simulations. But like I said, we have here one student that actually did that, Benjamin Vega. Benjamin simulate the Chilean system, the whole network of the Chilean power system with 100% converter interface generation. And we realized that actually the dynamic of the system was very fast as expected. No? So in that case, I'm not sure, for example, if it is valid to discard the dynamics of the network, for example, the stator transient in generators, if we have one synchronous generator at the end. I think in this extreme case, when you have maybe one synchronous generator, you need to change. But we have a task force in the IEEE, the task force from Monty, they are researching that now.
Yeah, I agree. And I think these are things we just have to keep an open mind and keep doing the research and see where we land. And because the other part of it is, I think, in the question, and I tend to agree, is it Benjamin who asked, if we go, so some systems in the world, I mean, you guys know this is nothing new, like the Aussies, for example, in Australia, do a lot of EMT analysis, but Australia, and I studied there, come from there, the entire Australian grid, if you put it all together in size, in terms of megawatt capacity, is smaller than Houston, Austin, and Texas put together. So how can you, what I'm trying to get at is, if you wanted to simulate the entire, say, Texas grid, or the entire US grid in EMT, God help you, it's just too big. So there's many problems here. There's the problems you just said, Claudia, which are very correct. Are we missing something? Then there's the problem of data management. There's the problem of size. So there's a lot of challenges. The good news is all you people out there have a lot of things you can do research on for many years to come. So
Exactly.
yeah, there's a lot of things to be balanced. And so it's always good to try to understand what it is we're worried about and try our best to go through the hierarchy of models, not to try to depend on just one type of model, because one size doesn't fit all.
Yes, thank you. I only can add that from the microgrid perspective, and relevant issue is the interaction of the controls in
Yes.
the different converters. And so this is today an issue, and perhaps this will be an increased issue at power system level. But this is a current topic for the type of analysis we need to do in microgrid level.
Yeah, I studied a couple of microgrid cases, and to your point, Rodrigo, microgrid, you do it in EMT. It's so small, you can put everything in EMT. Why bother doing anything else?
And this is an advantage, so you can really observe that. Perhaps this understanding will be transferred to power system issues to see the importance of this type of modeling. We will see.
And one of the things I think we don't utilize as much, and we talked about in the US many times, is still, it's hard to get people going this way, is the idea of equivalencing, right? So, for example, some things you want to study, you don't need to model the entire system. So you could just model, a small region and make an equivalence of the rest. Then you can do it in EMT. Then if you're looking at a very broad system-wide dynamic, then maybe you can have learned things, like you said, Rodrigo, from the smaller systems, that you can be confident that, okay, I can neglect these fast dynamics and I can make a big system model in my phasor domain tool and look at the big system things.
Exactly. So we come near to the end. We have 3 minutes and thank you again very much for your time. I want to combine the final 2 questions from Diego and Sam. They both refer to grid forming. The first one, if you can compare the voltage source converters with the grid forming inverter models, in the sense that they have or not the same capabilities in terms of voltage and frequency regulation. And Sam also asks, can you please elaborate more about the grid forming control? Which method is mainly used in the industry, please?
Yeah, so good questions. So first of all, in terms of capability, from everything I've seen, yes, they can both do all of the above: voltage control, frequency control, whole 9 yards. The only subtle difference is, for example, with the virtual synchronous generator, one of the things the vendors will argue is that because, and let me share my screen so I can maybe talk from a diagram, it's easier. So because you're in the voltage source converter, you're controlling this phasor much more tightly. What happens is that it truly gives you a emulated inertial response, right? Because as soon as the network phasor moves, there will be some power injection because of this angle variation. Whereas in the grid following converter, that's not true. You have to first sense frequency change and then tell the converter to go stick some more power into the grid. So it might be a fraction of a second slower, but we may be arguing over cycles there, and whether that's that important or not, I don't know. It depends on the system. I'm still not convinced that that is that important, but I may be proven wrong. That's the only thing that I can say will be subtly different between the two. Then the other question of, wait a minute, where have I got the, I'm trying to come to my slide. You were asking which one of these is more prevalent. So far, I'm just going to be honest with you, the couple of grid forming projects that I've worked on have had this technology, but that's not to say that these other ones don't exist or will not exist in the near future. So I don't know that I can tell you one's better than the other. I think time will tell, but all these, in at least research papers, you'll find all of these, and you'll find all of them show to behave well. In time, will we find that people will gravitate towards one versus the other? I guess time will tell. I don't know, Claudia, do you have a different perspective you want to share?
No, I think, like you said, no, I think we still don't have practical experience with grid forming converters, at least at high voltage level, not in microgrids. But maybe you know, Rodrigo or Pouyan, in microgrids, the grid forming converters that are used, which kind of model use are virtual synchronous machines or group-based control in microgrid?
Yeah, so I've actually worked on projects in microgrids and in large systems, and both of them had this virtual synchronous machine. And it's because it comes from a certain country, which many vendors come from. I won't say who, because you'll probably then guess what the vendor is. But let's just say the microgrid examples, real life microgrids I've worked on, they had this, and there's some real life on large power systems that also use this approach. But that's not to say the other approaches won't come in time, or maybe there are vendors looking at the other approaches. I think all of them are viable. All of them will make sense. We'll just have to give it time.
So thank you very much. I have one hand raised. So let us end with Mitchell Leon, or Leon Mitchell, please, if you can talk.
I'm here, yes. Thank you. Yeah, Mitchell Leon here. Yes, I want one question related or in line with the modeling, you know. My question is, what do you think about the cost simulation? I mean, use AMT plus RMES simulation at the same time, you know? Different software like Dixisland, like PCCAD, with it up, you can run this type of simulation. But I don't know if good idea use or not. What do you think in your experience?
Yeah, so that's an excellent question. Obviously, that tool is now being made more and more available, even in the commercial software platforms, like you said. I'll just share with you what I've seen in the industry. You know, okay, I won't mention them because I don't want to talk on their behalf, but one particular utility that has done that quite a bit in their system, they just shared what I would have expected, that, you know, it's nice, but if you, so here's the thing, they'll model a small region in EMT and then hook the, you know, RMS model on the end of it. But I asked them the question, well, instead of hooking the RMS model on the end of it and doing quote simulation, if you made it equivalent at that point, would you get a different answer? And the answer was no. It was probably just as good. So
yeah, this is my question. What is better? Use equivalent model or use an RMES model? What is better considering the time of the simulation, the result? It's not clear for me.
Yeah, and it's not 100% clear for me right now. I have not seen I have not seen a real life example where the equivalent was much worse than the co-simulation, because most places you can make an equivalent boundary reasonably. I guess if you got into a scenario where the system was so meshed that it was hard to define the boundary, then maybe co-simulation is better. But most cases today, defining the boundary is easy. But if defining the boundary becomes hard, then co-simulation is obviously better. Does that answer the question or no?
Yeah. Thank you.
Okay. And again, Claudio, if you have a different perspective, share.
No, I agree fully with you, Pouyan. There are many studies about this co-simulation, and I think the boundary is the key point, as you mentioned. I have nothing to add. I think we are in time now, so I would like, I really appreciate your time, Pouyan. We know that you don't have time, and you agree happy to present here today, so I really appreciate this. Yeah, I just wanted to
thank you, and thank you all for the opportunity, Rodrigo, Claudio, all of SERC. I think it's a learning opportunity for me too. We always learn from each other, and it's good to have these dialogues because I learn something new. We all learn together and grow together. So I appreciate it, and thank you for the privilege of being able to talk.
Yes, thank you, Pouyan. No, the privilege is on our side, and I really want to mention that for Chile, with the high penetration of renewals, the type of conversation and your insights are key for our energy transformation in the near future. So really, really happy to have this opportunity. I hope to all the people who attend that can contact you, and so we start more bilateral cooperation. Thank you very much.
Thank you, likewise. And Nicholas, thank you for keeping us all on track.
Nicolás, muchas gracias. Que tengan un buen día. Muchas gracias por asistir. Gracias, Claudia. Chau, chau.
Thank you. Bye.
Thank you.
Bye.
Everyone.
Listo, Diego. Me voy a cambiar